Okay, so I thought I would start by making a short introduction to the scientific background of the problem. During this talk, you will hear quite a few times, many times actually, this acronym, which is AMV, which stands for Atlantic Multidecadal Variability. Essentially, what is AMV? What is the Atlantic Multidecadal Variability? What do we mean by it, and why it is important for the global climate? The Atlantic Multidecadal Variability is a pattern of the North Atlantic sea surface temperature. It's a pattern of low-frequency variability. It has a typical time scale of around 60 to 70 years, so it's a multidecadal kind of variability mode. And the reason why it is so interesting or relevant for us, first of all, is one of the few examples that we know of a well-defined and multidecadal pattern. And you can see from this picture, essentially in the left panel, you will see a typical evolution of this mode, which is defined as the area average sea surface temperature in the North Atlantic basin. The Atlantic shows this prominent signal, which is overposed to a warming trend. And there are ways to separate the internal component from the global warming trend. And if we do this, basically, we end up with this AMV signal, and which has a typical structure, spatial structure, which is shown in the right-hand panel, and with this maximum loading over the subpolar basin, and this kind of a horseshoe pattern structure with an eastern kind of ring in the over, which touches the eastern side of the Atlantic basin, and it has also a subtropical lobe, and there's a kind of in the internal part, or in the central part of the Atlantic, there's a sort of a weaker signal. But the other thing that you might notice is that essentially this signal is unipolar. The sign of this AMV signal is uniform. In terms of polarity, the sign is constant, it's always positive, but there are some spatial dishomogeneities in it. And the reason why it is so relevant for the global climate is that it has been found that there's a number of different impacts over the global climate, and there have been studies showing that during a positive phase of this variability mode, there's an enhanced kind of increased Sahel precipitation, for example, which has clearly some societal implication. And then there are, of course, impacts all over the world, also including the European climate. Or thinking about the Mediterranean basin and the northern Europe, there are drier conditions over the Mediterranean basin and wetter conditions over the northern Europe, for example, associated to a positive phase of the AMV. And there's a number of additional impacts, for example, for the US climate as well. Some authors have connected the positive phase of this mode to the 1930s, 1960s droughts over US, including the dust bowls, for example. And again, other studies have connected the AMV to the hurricanes frequency over the Atlantic basin. So there's a number of reasons why this signal is particularly interesting and relevant for our climate, including the European and the Mediterranean region. About the sources of the or the causes, what determines this signal, there's still an ongoing debate. For a long time, we have been, well, the community, scientific community, have been relating the AMV to internal processes occurring in the ocean, and in particular to the Atlantic branch of the meridional overturning stream function, meridional overturning circulation, which is the Atlantic component of the global conveyor belt. But this was a kind of initial school of thought where there was not many other studies. In the recent years, there has been an additional or alternative kind of school of thought which have emerged, and in particular relating to the most recent part of the record, the ones that relates to the latest decades. There have been several studies pointing to a possible implication of external drivers, whereby external we mean something which is kind of exogenous with respect to the internal variability of the system. So something arising from the, for example, aerosols, but other studies also point to possible impacts of volcanoes or solar variability. So there has been some challenge going on. Many studies have been starting to challenge the dominant paradigm so far, so that the AMOC may or may not necessarily be the major driver, and other factors may come into play. So currently we have these two kind of branch in the community, and it is important to remark that they do not exclude each other necessarily, and it might well be that perhaps these two patterns or these two, let's say, factors are active at the same time, and they're both important, but probably they are active in different phases of this cycle or this variability signal. In this specific study, we tackle not the whole thing in a way, but we decided to focus on one specific part of the cycle. In particular, we decided to focus on the cooling, which occurred around the middle of the 20th century, between the 1940s and the middle of the 1970s. And the reason why we do that, this is a particularly interesting epoch to focus on, because during the same period, the global mean surface temperature of the planet underwent a kind of hiatus, meaning that the sea surface temperature at the global scale were not increasing at the same rate, at the same pace as they were increasing before and as they would have increased later on. So there was a kind of hiatus. We're familiar with the word hiatus because it has been evoked recently to refer to another hiatus, which is the one which occurred at the beginning of the 21st century, of this century. But this is a middle 20th century hiatus, and it might be interesting, we thought it might be interesting to look at this specific event, during which in the North Atlantic there was a significant cooling, as you can tell from the lower panel in this figure, which shows the pattern of the cooling, and again strongly resembling the AMO or AMV-like structure with the largest loadings in the subpolar basin, but at the same time there is a kind of horseshoe structure again. So the typical approach that we used in this kind of studies, because it's very difficult to analyze this kind of phenomena relying on observations, because the observations are scarce and not sufficiently sampling the whole climate system, the modeling approach turns out to be very valuable in this kind of case study. And what we did was to apply a kind of detection attribution approach. But before I move to the next slide, I just want to make a short list of the possible hypotheses that were formulated at the time to explain this specific event. And some authors have suggested that there's a number of potential candidates that might have explained this cooling, some pointing to the existence of the Great Salinity Anomaly, which was a large freshwater anomaly that might have determined this slowdown, or determined through affecting the thermohaline circulation and determine this slowdown in the temperature. The others have pointed to the AMOC slowdown itself, as probably due to some warming in the climate, warming of the atmosphere. Also, volcanic eruptions were invoked as another possible driver, because during the early 60s, in particular, there were some events associated to this Agung volcano. decline of the solar radiation as well, anthropogenic aerosols. So as you see, there's a wide range of potential causes and candidates, but no one of those so far have emerged as the main or major driver. So as I was mentioning before, the approach that we decided to follow was the one that it is used in the detection and attribution community, which consists in using a hierarchy of climate simulations ranging from historical kind of simulation where all kind of forcings are essentially used, natural and anthropogenic, and gradually narrowing down to a subset of forcings, including anthropogenic forcings, for example, only, down to very idealized experiments where single forcings were used. By AA, we mean here anthropogenic aerosols, or individual single forcing using only greenhouse gases. This approach, it's very useful, and it's, I mean, what we can do with models. Basically, we can gradually reduce the complexity of, let's say, of the setup of your experimental setup, up to the point that we manage to somehow restrict or reduce by reducing the number of forcing, we basically can converge towards the possible drivers of a given phenomenon. Just a little bit of terminology. By natural forcings, we intend volcanoes and solar variability, whereas by anthropogenic forcings, we intend here greenhouse gas, anthropogenic aerosols, land use changes, and ozone. Okay, for this study, we use as many simulations were available from the CMCC archive, and I just summarizing in these two tables which models did we use, and what was the size and the number of simulations that were used. It is important to remark here that because we wanted to focus on the forced component of the overall variability, basically we want to filter out an internal variability component, and for these reasons we only use those models that had provided a minimum ensemble of 3 members in this case, of realization of the historical climate. So in the first, well, in any of these experimental sets, we have only allowed models that have provided an ensemble of simulations. And the reason is that by using an ensemble, we can basically isolate or identify the forced component through an average across the whole set of members. And in this way, we can be assured that we are ruling out or excluding from the signal the internal variability component. Okay, so we started from the broadest set of forcings, which is the ones that are used in a so-called historical climate simulations. So here, everything is in place. We have both natural and anthropogenic. And if we look at how does the AMV look like in observations, which is the solid black line, and we compare it to the CMCC models in the historical simulations, what you see is that there's a remarkable sort of coherency or agreement between the simulated AMV and the observed AMV for the 20th century. And this was kind of surprising in a way, because we were not expecting to see that the CMCC models, once we have removed, as I said before, the internal variability, were still able to reproduce this feature of the climate variability of the Atlantic Ocean. So essentially, what you see here is that the solid red line is the multimodal ensemble average, and the shading around it shows the envelope of the multimodal ensemble. And interestingly, you see that the envelope, the multimodal ensemble envelope encompasses or includes, to a large extent, the ups and downs of the observed sea surface temperature in the North Atlantic. This is quite interesting result because it shows that because we have averaged across so many different realizations of obtained through model simulations, that what we are looking at here is the only forced component. So this means that there's a large fraction of the observed variability in the North Atlantic that is explained through the only forced variability, and it does not include the internal variability of the system, which is the component which is typically associated with the ocean dynamics, which is generally uncorrelated when we analyze such a large ensemble of simulations. If you look at the spatial structure associated to this signal, in particular, if we look at we take a composite and we take the average of the sea surface temperature during a warm phase of the oscillation, and we subtract from this average in the warm phase the average in the cold phase, and we just make a composite of the warm minus cold phase of this of the specific time period that we are analyzing, and you see that the modeled pattern has a strong resemblance again with the observed pattern. So the modeled pattern, which is the one in the top right, you see obtained by using 69 different members, again reproduces quite well this horseshoe structure with maximum loading over the subpolar basin, and there is again there's a horseshoe touching the eastern side of the Atlantic. There's this tropical, subtropical lobe, and there is a cold lobe in the central Atlantic. And this is essentially very similar to what the observations also show for the same period. Another interesting feature that you might notice, both in the OBS and in the model, which is what captured here, is this kind of connection with the Mediterranean area. Okay, so we went further than that in order to characterize the uncertainty within the model, because in the general picture you won't be able to distinguish which model is doing what. And if you look at one specific diagnostic that we have introduced over here, which is described mathematically in this lower part of this picture. And this TR diagnostics was introduced to define the deviation of the North Atlantic sea surface temperature from the baseline mean computed over the initial 20 years of the period from 1930 to 1950. And this was introduced just to somehow better disentangle the individual behavior of individual models. And if you look at the right-hand pattern, sorry, the right-hand plot, you see that the models tend to cluster around very distinguished behaviors. So there are models that contribute to the good skill of the multimodal ensemble mean, which are the green ones, and they capture fairly well the inception of this decline in the sea surface temperature in the middle of the 20th century. They reach a minimum which is slightly before the observed one, but then there is an uprise afterwards, and that's a very good, I mean, qualitative, but not only qualitative agreement with the observations, which are in black. There's another set of models which are in this light blue, which also capture well the inception, the onset of this decline, and there is a, but they fail in perhaps in capturing the right phase when the temperatures start to grow again. And there are models that, like the red ones, that simply with some ups and downs, but basically reproduce a growing temperature trend, and they seem to basically to ignore what the observations actually show of this cooling that we actually observe. And we define an additional metric just to compare these individual models to the OBS. So a metric is essentially a number that we can directly relate to the OBS, and I won't spend much time to describe it, just to show how models through this metric can better, I mean, there's an even more clear separation between model behaviors, and the green models, again, are the ones that better agree with the OPS, which are shown by this black asterisk over here, whereas the red ones have the opposite behavior, and there is the light blue line in between, according to the metric which is defined here, which is essentially the difference. There's a sort of low-pass filter of the diagnostic, which is shown in the left panel here. And so there are three well-distinguishable behavioral clusters which are identified within the CMIP5 population. If we use this information, then we can restratify the model information into subsets according to the cluster that we have just identified. And if we call these three clusters A, B, and C, and you repeat this composite, and you will see that depending on whether we only pick the models A, which are the ones that fade in reproducing the cooling, or we pick the models B, which are the ones that capture well the model behavior, well, you will see that the outcoming pattern has a very different kind of similarity with the OPS. And if you include all of them, which is the A, B, C, which is in the upper left panel, you'll see what happens if you do a multi-model average, which is, again, is not doing a bad job at all, but you can tell that this good job is actually due to the contribution of patterns B and C, whereas pattern A it turns out to be a complete failure. Okay, so the question is, provided that we can explain that, basically we can explain the AMV signal as a feature of the forced variability of the system rather than to the internal variability. And the question now is, well, what kind of forcings is that? It might be a natural forcing like solar variability or volcanic forcings, but it might also be equally well an anthropogenic forcing. And again, the detection and attribution approach help us in disentangling the roles of these individual forcings. So if we use only anthropogenically forced simulations, so now we are only using greenhouse gas aerosols, land use, and ozone forcings, well, basically this is the picture that we get. The AMV observed, AMV is again the black thick line, whereas the bluish curve is the multimodal ensemble envelope, and the solid blue one is the multimodal ensemble mean. And what you, first of all, you notice is that this envelope is essentially flat during the first half of the record, of the modeled record, whereas in the second half of it, there's a hint that the envelope managed to capture this relative minimum in the observed record. So where is this coming from? This is very interesting to see. And again, if we apply our approach we apply our usual diagnostics and metrics, clearly we see that even under purely anthropogenic forcings, the models again split apart in three different clusters, the same kind of cluster that we had identified in the fully forced simulations, where we were including all the forcing, essentially natural plus anthropogenic. But now we are only using anthropogenic, and again we see that there are a few models, a handful of models, in this case a very little subset, because it is only made of three different these green models that manage to capture the phase of the sea surface temperature decline in the middle of the 20th century. And then again, so there's a different relative weights of the different cluster now, because the cluster A, which is the one with the red curves, is now having a prevailing role in the overall ensemble. And this has implication when we compute the multimodal ensemble mean, because it means that the models that fail in reproducing this signal will be much more important in dictating the multimodal ensemble response. So we need to be cautious when using a kind of a middle point approach and thinking that the multimodal ensemble might be the best option, because if we look at more in detail at individual phenomena, it might well turn to be that this is not the case. And we apply, again, we re-stratify the models based on this information in cluster A, B, and C. And if you look at the ensemble B, for example, the models that capture correctly the decline indices of surface temperature, you see that the cluster B has an outstanding similarity with the observations. Also, cluster C, which is not a real cluster because made of one single model, has a very good skill in reproducing some of the feature. But for example, if you look at what happens in the in the Nordic seas, you see that the anomaly in the cluster C is completely wrong, whereas cluster B is much more faithful to the observed pattern. Whereas again, cluster A turns out to be a complete failure. And if we merge all of them, so if we do the standard multimodal ensemble mean, you see again this the multimodal ensemble mean will be very much influenced by cluster A, and there's an abundance of blue all over the place. And we know that this is because the cluster A is much more represented. So there's an issue here when you're using multimodal ensemble. Okay, so now we're basically narrowing down to even a smaller set of forcings. And the question is, if it were anthropogenic, as it seems to be, what kind of anthropogenic would that be? And in order to address this question, we decided to use these very idealized experiments, but still very insightful experiments where you use one single individual forcing. What I'm showing here is exactly what happens if we only use several models, but all forced with anthropogenic aerosols standalone. And we know that the radiative forcing associated to our aerosols, to anthropogenic aerosols, is by and large, overall, largely determined is a cooling. It has a negative radiative forcing. And therefore, what you see consistently, you see that most of the models, with one outlier exception, which is this blue one, but all of the models essentially reproduce a cooling if we only use the anthropogenic aerosols. So they all agree to some extent to the observations, except that now this is kind of an idealization, and we need to keep this in mind because we know in the real system there were all sorts of forcings working at the same time. But the reason why we use this kind of idealized setting is because it allows us to look at how a climate system responds one by one to individual drivers. But what is also interesting to look at is the space structure associated to this forcing. So this is in the right panel, you see that this is the multimodal ensemble. In this case, there's no problem in using the multimodal ensemble mean because all the models basically agree. And what is interesting to notice is that even though the sign of the change, by and large, you see right all over the place, but there is an area here over the subpolar basin where the tendency has an opposite sign. So the climate system is not responding homogeneously to the aerosol forcing. This is not completely new because we know that the aerosols are not mixed gases. They have regional features because they are concentrated over certain areas, which typically coincide with the downstream region of areas like North America in this case, where there is a high industrial activity, and this determines a large plume of aerosols that basically, following the westerlies, the dominant winds, span the Atlantic Ocean. If we do the same exercise, but now sticking to models which only use greenhouse gas forcing, you see, not surprisingly, perhaps, that all models, when forced with only greenhouse gas, agree that the basin average response is a warming one. So all the models basically go up in the temperature, and they do not reproduce at all the cooling. This is kind of expected. What is less expected, perhaps, again, is this inhomogeneous response of the multimodal ensemble mean. where you see there's an abundance of blue all over the place, but there is again the subpolar gyre over here that is showing some less intuitive response. And you see that while all the model, while everywhere in the Atlantic temperatures are increasing, well, this is not the case for the subpolar basin, where the trend is either neutral or maybe is even the opposite sign if we look at individual models. In this case, it's a kind of white, which means that there is no trend. But this is again this multimodal is the multimodal ensemble mean. So wrapping up these two in single experiment, this set of idealized forcing experiments, what we see here is that these two forcing, aerosols and greenhouse gas, seem to be kind of orthogonal to each other, broadly speaking. You see that the pattern have opposite sign, the pattern of change in the SST has opposite sign, and but there is a kind of inhomogeneities over the subpolar basin, which is a commonality also shared by both ensembles. In order to have a better understanding now as to why models clusterize, why we have seen that there are single and different models. If we look at individual models, this is very interesting because then we can have a better view of how the individual forcings act on one single model, and we can better understand instead of looking at the multimodal ensemble. So in this case, I picked one specific model, which is the Australian model, which has undergone through the whole set of forcings, and the three panels show what happens if we force this model, including both aerosols and greenhouse gas. And what happens if we only use aerosols, and what happens if we use only greenhouse gases. And although you see that the anthropogenic response outside the subpolar basin, which is identified by this box over here, seems to be largely determined by the action of our aerosols. But if we look at specifically at the subpolar basin, you will see that there is a very strong similarity with the greenhouse gases forcing only experiment. And this is somehow telling us that the aerosol and greenhouse gases are both important in shaping the overall anthropogenic response of a given model. And therefore, they are both concurring to the overall pattern. There's no one dominant driver, but they both important, and they also project onto different areas of the North Atlantic. In particular, the greenhouse gas seems to play a major role of the subpolar basin, whereas the aerosols are not able to explain what happens in the subpolar gyre, but they seem to fit quite well and explain what happens, for example, in the subtropical and tropical Atlantic, and also in the Mediterranean area. So a possible conjecture about the middle 20th century North Atlantic cooling. It seems that the middle 20th century cooling results from a combination of anthropogenic aerosols cooling over the tropics, subtropics, and greenhouse gas forced response in the subpolar basin. In here, I'm mentioning the thermohaline circulation slowed down because there have been works showing that in a warming climate, the slowdown of the thermohaline circulation is a plausible response, and by this slowdown carrying less warm water to the northern North Atlantic may determine a local cooling of the system. So basically, this pattern appears to be consistent with such an explanation. Remembering that this pattern that you are looking at here is the difference between the warm phase and the cold phase. So it means that the subpolar basin was much warmer during the let's say 30 to 50s period with respect to the 60 to 80 period. So the subpolar gyre underwent a major cooling and even larger, at a larger rate with respect to the other areas. But as you will see, the anthropogenic forcings appear to be quite able to explain the cooling that we see in the Alps. Another element is why do the models cluster, and a possible conjecture about the reason why models group together into individual groups, behavioral groups, may be given by looking, instead of the normalized, the index that we were referring before, we look at the numbers, the curves in these two panels haven't been normalized. The reason why we were normalizing it before, because we wanted to get rid of the individual models' biases. But if we look at how different models truly respond to the anthropogenic aerosols, we see that there are certain models that are much more responding to the increase of the anthropogenic aerosols with respect to the others. And this large spread in the response to anthropogenic aerosols is dictated by the way single models represent, for example, the cloud microphysics and the way clouds respond to aerosols. Certain models do not include this indirect effect of the aerosol. They only include the radiative effects, which is due to the backscattering of the solar radiation associated to the aerosols. And this might determine quite a large spread in the model behavior, whereas greenhouse gas forcings have response is much more uniform. But the aerosols seem to ones that determine the widest uncertainty in the response, and depending on how individual models respond to aerosol and greenhouse gas, a model may finally end up in one cluster or in another one, because it might be that the greenhouse gas forcing is more effective than the aerosols, or vice versa. So it's a quite complex pattern which is emerging over here, but I want to kind of, coming to the end of this talk, I'd like to show sort of synthesis of the AMV and the possible forcings that might act at different stages of the AMV. So according to our findings, it looks like this more recent half, or the second half of the 20th century, forcing was mainly affected by anthropogenic forcing, including both aerosols and greenhouse gases. But that doesn't rule out the involvement of natural forcing, for example, during the first half of the 20th century, where in fact it seems that, for example, from other studies we know of, that the solar radiation might have been implicated in this growth of the sea surface temperature in the Atlantic. And above all, again, we cannot rule out the role of the internal processes, because the AMOC is also at work, and it might well be that if we look at the pre-industrial age or paleo data, where we also know that there is a low frequency variability in the Atlantic, the ocean dynamics and in particular the AMOC might have played an important role. There's a very long debate on this, but we need to focus on, we decided to somehow have this piecewise approach and selecting what specific event and focus on this specific event, just to be to verify whether climate models are able to reproduce most recent part of the record, for which there are more observations. So conclusions, I will be very quick over here. Essentially, the picture which emerged, as I said before, is that anthropogenic drivers, as I say, appear to play a relevant role during the middle 20th century cooling. There are clusters, as I just say, and then these clusters, the behavior of the models point to some fundamental differences in the way individual models respond to prescribed natural and anthropogenic forcings. The estimates based on the large size of the multimodal ensemble mean climatic variables may be the midpoint of fairly distant model populations, and we need to take this element into account. And also the uncertainty associated with alternative aerosol and greenhouse gas emission scenarios should be also accounted for when we design a common protocol for example, for coordinated decadal forecast experiments, because, I mean, we need to take into account the fact that the uncertainty is not just related to how we initialize a given forecast or which model we use, but also on how the let's say, anthropogenic drivers may change in the near future. And this is important not only for the standard climate projections, but also for, in particular, we've seen today for the decadal variability, which is more in the realm of decadal climate predictions. And I say I will stop here